Okay, thanks for having me. This research is on adaptive testing on a conditional mean at a point. So here we're interested in confidence interval for a conditional mean at a particular point. In particular, we're interested in the case where this point may be on the boundary. So I think that most people in this room are aware that this describes a lot of empirical applications in econometrics. So regression discontinuity and the many applications that fall under the label identification at infinity. So here, it turns out that under these conditions, you don't need to know the amount of smoothness to at least get a one-sided confidence interval in a certain direction, as long as you're willing to give up the log-log n term. And it turns out that the log-log n term is needed in a certain precise sense. So this paper uses monotonicity conditions to achieve adaptivity. So the monotonicity is also very much tied in with the one-sidedness and the direction of the one-sidedness of this confidence interval. And there's a sense in which you need some sort of shape restrictions to get an adaptive confidence interval. And this is a paper by Lowe, 1997, that formalizes this. So in particular, even if you can estimate the optimal or figure out in some way the kernel bandwidth that's optimal for estimation, there's a sense in which you can't know which smoothness class you're in the sense that you would need to get a confidence interval. So in particular, if you don't have any smoothness assumptions or anything, if you want to have a confidence interval that shrinks at the two derivatives rate when you have two derivatives and in the one derivative rate when you have one derivative, you can't do that. It just always has to, if you only know that it has at least one derivative, you always have to, it's always going to be as big, even in the two derivatives case, as in the one derivative case. So I think that it's an interesting research program to think about other types of shape restrictions that you can use to get adaptivity. But the point is that you're going to need some sort of shape restriction to do so. Okay, so the implementation of the test that achieves this, the confidence region that achieves this, is actually very, very simple, and I'll show it graphically. You do a bunch of, I'll do k-nearest neighbor estimators, but you can do kernel estimators. You kind of pick the best one that gives you the best confidence region, and you use a certain adjustment for, I'm calling this bandwidth snooping, but we still don't have a version of this paper circulated yet, so we can use a word other than bandwidth snooping if people have suggestions. But use this adjustment for the fact that you looked at multiple bandwidths, and in this paper with Michael Kolesar, which we're planning on circulating soon, we show how you can do the adjustment, and it's actually very simple. We actually have tables for the critical values. Okay, so there's some limitations to this. I guess I've already gone over most of these, and it'll become clear why we need them later in the talk. Here, so one thing that I haven't gotten to yet is that this is for ranges of adaptivity of pretty non-smooth conditional means. This is also tied in with the monotonicity assumption. You could kind of play around with concavity and using more derivatives and stuff like that, which I think would be also an interesting research program. Okay, so there's a lot of related literature, although as far as I can tell, none of them have treated this particular problem. Right, so here's the formal setup. So we're interested in inference on a conditional mean at a point that's at the boundary, well, for now we'll just assume that it's at the boundary of the support. So this is a very idealized setup. You can relax all of these normality assumptions and so forth. But just to get the idea of what's going on, let's suppose that we'll actually get some exact finite sample results. So we'll assume that we have normal errors with a known variance conditional on x. And in fact, I'll just make it constant through a lot of the talk. So xi has a density, or actually there's an additional assumption that it has a positive density bounded away from 0 on the set 0 epsilon. In the cases where you have identification at infinity and the density is going to 0, or it's actually at infinity rather than a finite point, you can transform the density back to, say, the unit interval, and the stuff that I'm doing, you don't need to, you can do that after the transformation. And the smoothness conditions will kind of come from the rate at which the conditional mean approaches 0 and the tail conditions on the distribution of x. So anyway, if you're interested in this like Andrews and Shafkin's Heckman Mansky bounds type of thing with identification to infinity, you can play that game. I have, if anybody's interested, you should ask me. I have a section in another paper where I did that in another context with moment inequalities. Okay, so the key restriction here is the monotonicity restriction. It's just kind of a weak monotonicity restriction in the sense that it doesn't have to be monotone from each point from one point to another. It just has to be that this function is less than or equal to what it is evaluated at 0 whenever you get above 0. Here 0 is the point that's on the boundary that we're just normalizing 0 to be the point that we're interested in. So we're interested in a one-sided test for this conditional mean evaluated at 0. So the null hypothesis is that this conditional mean evaluated at 0 is less than or equal to some theta naught. And of course, we can invert these tests. And this will give us a one-sided confidence interval, some c hat to infinity, where we, once theta naught gets above c hat, we fail to reject, and we report that as our one-sided confidence interval. Okay, I've talked a little bit about the generalizations to regression discontinuity. There's actually a neat, I think neat, generalization to a particular problem on inference on the proportion of nulls in null hypotheses in a multiple testing setup. But let's just talk about the conditional mean econometrics examples for now. Okay, so for simplicity, let's just have an even more simple model where we assume that the conditional variance is known and constant. So the sigma squared of x is just equal to some sigma squared, which we assume that we know. So here's the approach. So we take a k nearest neighbor estimator for a given k, and let's call that g hat k. So that's just what this is on the second slide, the k nearest neighbor estimator. So we're just ordering the x's. This x circle k, or x parentheses k, is just the kth smallest value of the ordered x's. And we just take the sample average of all those x's that are less than or equal to, or the y's for the x's that are less than or equal to that. So that's an estimator for a given k. We don't know what k to choose, but by the monotonicity assumption, we know the direction of the bias, right? Under the null, this bias, this expectation of g hat k, under the assumption of monotonicity, has to be less than or equal to this g of 0. Here, just for any given k, we could get a valid test just by ignoring the bias and just reporting the test for that given k. But here we want to choose the k that gives us the most power, so the tightest confidence interval, which depends on the smoothness of g, which is a problem that I was motivating at the beginning of the paper, of the talk. And so to do this, what we do is we have our test statistic just look at a range of bandwidth. So for a given k lower bar and k upper bar, which I'll actually just define for simplicity to be 1 and n, we'll just take the maximum over k in that range of the standardized values of g hat k minus the theta that we're testing. Okay, so it turns out that we can actually get valid with this with the normality assumption and the known variance. We can get critical values that are valid in finite samples here. So how do we do this? So basically, what we're doing here is we have our data, we have our x's, and we've ordered our we have our x1 or whatever, and so forth. We're plotting our y's. So let's call y sub I colon n the value of yi that's with the same observation as the ith smallest value of x. So these aren't actually, just to be clear, they're not order statistics of the y. They're just ordering the y's by the x. So we have our y1 out of n. We have our x2, maybe an x3 is a little bit closer here. y2 out of n, y3 out of n. And more data points and so forth. And what we're doing is, we're just translating this down to, for every value of k, we're just going to the corresponding x, and we're getting we're averaging more things, and we're getting our, our g hat k, so our g hat 1 and our g hat 2. So if we think about what we're doing here, right, and then so we're just doing the test for each one. So if you think about this test statistic, this is just taking the maximum of these. So now I'm just rewriting this nearest neighbor estimator as a sum from 1 to k of I from 1 to k of y I out of I colon n. Well, then we can just see if we just let z1 through zn be an IID normal 0, 1 sample independent of the data. This just has the same distribution. Once we condition on all the x's, right, so yi out of n conditioned on all the x's is distributed normal with mean g of x parentheses I and sigma squared. So this is just, we can just replace these with, sigma times a normal 0, 1 random variable plus its mean g of xi. But then under the monotonicity assumption, we know that under the null that theta is greater than or equal to g of 0. It's also greater than or equal to g of x for all these larger values. And so replacing this with 0 will only make us more conservative. And so we can just, as the least favorable critical value, just use sigma times the distribution of the maximum of these normalized sample means of normal 0, 1 variables. And that's something that we can actually table. It's just a distribution that depends on k lower bar and k upper bar. Okay, so we just let C alpha k lower bar k upper bar be the 1 minus alpha quantile of this maximum of the normalized sample means of these IID normal 0, 1 random variables, and we just use that as our critical value. And that gives us a test, use sigma times that as our critical value. And we just use that. That gives us in this idealized normal setup, gives us a finite sample valid test. And in the paper with Michael, we work out how you can get these critical values asymptotically for other kernels. It turns out that it only depends on the kernel and the ratio of the bandwidths. And we're also in the process of tabling all those. Okay, so you can think of this, I think this has a nice interpretation in terms of what I'll call bandwidth snooping, but I'm also open to suggestions for what to call it. So let's just think of, so one point of view on conditional mean estimation is that you can't really do it. You can't really estimate the conditional mean. All you can estimate is kind of what you're unbiased for. So let's condition on all the x's and think about what we're unbiased for when we have the k nearest neighbor kernel. It's just estimating the sample mean of all of the conditional means evaluated at those first ordered points of the x's, right? So what we're doing here actually is we're constructing a one-sided uniform confidence band for all of these sort of pseudo parameters. Right, so what I'm saying here is that this g hat k minus this critical value, that's going to be less than or equal to this theta tilde of k that I've defined. So with probability 1 minus alpha, we'll have simultaneously for all k between the lower k and the upper k that's in that confidence band. And so what we're doing is we're just, well, if you sort of just invert the rejection statement that I had in the previous slide, we're rejecting if theta is, right, if the lower confidence band is greater than theta for some k. So in other words, if the maximum of that lower confidence band is greater than or equal to k, so this just gives us our confidence interval associated with this test, which is just using the most favorable point of that confidence band. Okay, and as I mentioned, this an asymptotic version of this with non-normal errors and with other kernels, which is a paper that's in progress with Michael. So here, I'm just kind of plotting. This is just one instance of a data generating process with all of these. This is the data generating process here. So here, what you can do is you just take this. This is this lower endpoint of the uniform confidence band is on the dotted line. The solid line is the point estimate. So you can interpret this as a uniform confidence band for these biased things, but then we know the direction of the bias under the null. We just take the most favorable one, which is here around k equal 300. Yeah, so it has a simple graphical interpretation. And you can also think of just these plots as just kind of a way of summarizing. But another thing you can do is just plot the two-sided version of this, and it kind of gives you a sense of how your estimates change with, in this case, k, or with the kernel case, the bandwidth. And then you can use the monotonicity just gives you one interpretation where you can use it to pick these bandwidths that are optimal in a certain sense. OK, so what is the intuition for this penalty for this log n term? That's the penalty for adaptation. So intuitively, there's a bias variance trade-off sort of in the power calculation that comes from that. But intuitively, it comes from so the penalty for adaptivity, right? If we knew the optimal k for our k nearest neighbor kernel, then we would just do the version of this where k lower bar equals k upper bar equals that k, and then that would give us a smaller critical value. So intuitively, if we want to kind of have adaptivity over the range that corresponds to k lower bar and k upper bar, the penalty for that adaptivity in terms of power is this thing on the top bullet point, the C alpha k lower bar k upper bar versus just C alpha for just the two k's being the same, which is 1.64 or whatever for alpha equal to 0.05 for a one-sided confidence interval. OK, so by the law of the iterated logarithm, we in fact have that for all values of alpha, if we scale this by √2 log k upper bar, as k upper bar goes to infinity, that converges to 1. So that's the law of the iterated logarithm. It's an implication of the law of the iterated logarithm from probability theory. So the penalty for adaptivity is root log n, root log k upper bar, but it's going to be proportional to root log n with the rates that k upper bar is going to increase. So intuitively, this is telling us that it's small. It's in the sense that log of n is small, log of n is very small, and then if you take the square root of it, it's very small. So in some sense, this is good news. Now you might say, this is kind of ridiculous. This is just like really large sample stuff where you have a bunch of logs. This is just kind of crazy. But you can actually just calculate these. So I'm doing this in finite samples now. You can just calculate these for different values. I don't have the graph with me here. But you can assess the penalty for adaptivity, and depending on the critical value, you can just see that it's moving 1.645 up to say 2 or whatever it is for the given values of k. Okay, so to translate these into power results, so let's define the notion a little bit more formally, the notion of adaptivity. So as I mentioned, we're going to be adaptive within a range of relatively non-smooth smoothness classes. So for a given beta and a given L, let's define the Hölder class of functions associated with that beta and L to be those for which those functions g for which g of x minus g of x prime is less than this Hölder modulus of continuity for each x and x prime. So we're just saying that, and in fact, we only need this at 0 basically. But basically, we're just saying that this for some beta, which is going to be less than or equal to 1, the function behaves like is more smooth than x to the beta near 0. And as I was saying before, you can get this quite naturally, really for any value of beta, from these different tail conditions when you have identification at infinity type things, or in the case where you're just at a finite point and you have a density that's bounded away from 0 and infinity, then you just get it from the conditional mean itself. Okay, so the additivity is that our test has high power whenever you move away from the null by at least this well, this much log n over n to the beta over 2 beta plus 1. So this beta over 2 beta plus 1 is this familiar thing that pops up from bias variance trade-offs in non-parametric estimation. And you can see where the log n came from. OK, so to state these results, let's we're going to subscript everything by g. So we're going to talk about uniformity. And we're going to want our results to be uniform in certain Hölder classes. And then when we say that we're optimal, we're going to be saying that if you want to have uniformity over a certain range of Hölder classes, that you're going to need to pay this log n term. So we're going to take infs and so forth over these over g in these classes. OK, so the first result is that you take the test above. Just for concreteness, take this k lower bar equal to 1 and k upper bar equal to n. So the first display here is what I already told you, just that this for any n, this has correct size. The second display is that if we take any epsilon greater than 0, so just any range of epsilon to 1, where epsilon is greater than 0, and we consider these smoothness classes for those betas in that range, then so we want this uniformity, so we have these infima inside of this lim. So the limit as n goes to infinity of the worst case power that you can get when you're in this class for some g, and for which for some constant, there exists a constant c star, well, which you can also calculate, but there exists for a constant c star, you're at least log n over beta to the 2 beta plus 1 away from the null. So in other words, uniformly over these Hölder classes, you're shrinking at the one-sided confidence band is shrinking at the optimal rate. So power is going to 1 uniformly over these classes. The fact that the power actually goes to 1 rather than just for a constant here has to do with the fact that because of the law of the iterative logarithm, everything is concentrating, all the quantiles are concentrating at this root 2 log n. OK, so it's uniform over this range. The epsilon I think is not too bad because, of course, if epsilon is 0, then you might actually just be able to take epsilon equal to 0 here. I guess it would kind of depend on, then you would have beta getting, the rate gets arbitrarily bad anyway. So this is the notion of adaptivity or uniformity over beta that we have. The proof of this part is pretty intuitive and easy. It's more difficult to show that it's necessary, I guess, which is the next theorem. But basically, this is just like Pagan and Ula or Hölder or whatever non-parametric textbook you like, and we're just doing the k-nearest neighbor version of it, and we're replacing, so when we do the bias and variance trade-off, we're replacing the root n with this critical value that's root log n over root n, and that's then it's just pretty much the same thing. Yeah, so this is just calculating the drift and variance terms. It turns out that in this precise sense that's made precise in this theorem, the log n term is actually needed in order to do uniformly well over these smoothness classes. Let phi sub n be any of sequence of tests that's asymptotically level alpha whenever you have this monotonicity condition. In fact, you can also add in these smoothness conditions under the null. You can even make the null just that g is always equal to theta naught. If we take any non-trivial interval between 0 and 1, so take a beta lower bar strictly less than beta upper bar less than or equal to 1, and then we take that test and we ask how well does it do when we scale by this rate that we achieved before, log n over n to the beta over 2 beta plus 1. Well, there exists a constant such that the test has to do constant greater than 0, such that relative to that rate, for one of those values of beta in this interval, you're going to have trivial power asymptotically the same as the size. So we know that if we had just chosen the k with the optimal, just chosen k optimally using prior knowledge of beta, we wouldn't have needed this log n term. You can just use the usual bias variance calculations. And the fact that that would be optimal, it turns out that if we want to do this simultaneously for a range of betas, that we need this in a formal sense. So I won't go over the proof, but the basic idea I think is pretty intuitive. Basically, you just find an approximately least favorable distribution under the null and an approximately least favorable distribution for each of these, for a grid at least of values of beta. And then you ask, how well can I do in terms of weighted average power for that value, for that grid where the grid is increasing? So that's a bound on the worst case power, but it basically amounts to bounding the power of the average likelihood ratio test for that prior, so to speak, over the approximately least favorable prior over the alternatives. Okay, so just comparing this to some results from the literature. If beta is known, you can drop the log n term, and it's optimal. These log n terms pop up in other cases in the literature where we have adaptive inference and testing problems. And in fact, this idea, the argument that I just mentioned, what's new for this problem, but it's been noticed in other settings and proven in other settings that you actually need this log n term. And I think Spokane 1996, which is, I think, for LP testing in the LP norm or something like that, is the first reference that I'm aware of. It turns out that for adaptive testing on the interior of the support, you can do better. You don't need the log n term. So I was interested to find out that for these types of regression discontinuity and identification and infinity problems, we have to pay this additional relatively small price. I guess the bigger price that we're paying is that we can only have one-sided confidence intervals, whereas if you're on the interiors of the support, you can just, well, it's kind of obvious. You can just do the same thing on both sides, and then you can get a two-sided confidence interval. Okay, so as I was saying, the log n stuff and the rates might seem a little bit obscure, but I think that there's a very clear prescription that comes out of this for empirical work, which is that in this setup, there's a certain sense in which you just can't just estimate the optimal bandwidth and use that for your confidence interval without any sort of correction. So we know that we can't do that in general from the Low paper that I cited earlier, but we might think that, well, with this, with this monotonicity, then we could somehow just estimate it quickly enough. Well, in a uniform sense, if you want to do well in all these cases, there's a sense in which kind of the best thing that you can do is just kind of look at all of the bandwidths in this range and just kind of see what they give you, and then just use the interpretation that you get from monotonicity to pick the best one. So in particular, cross-validation and all these other things that work well for global estimation, for example, they might not even control the size, and they can't be optimal in this setting. So you can think of this as a justification for what Michael and I are proposing in this work in progress, where we say that you should compute this snooping adjustment. This is kind of saying there are cases where you just kind of just have to snoop. Okay, so I mentioned that identification and infinity and regression discontinuity are kind of the main applications in econometrics. I think it's pretty clear how this is going to generalize to the regression discontinuity setup, right? So let me actually try to talk a little bit about, we take the difference on either side, and we get the same optimality results. So here this application is to a multiple testing problem where people are often interested in, usually interested in estimating the proportion of null hypotheses in order to plug this into a procedure that controls false discovery rates. And here I'm interested in doing inference in it, just sort of noticing that you can use the same methodology. And here we're interested in inference on a density rather than on a conditional mean. So the setup is that we have p-values from independent experiments, Under the null, they're distributed uniform 0, 1. Under the alternative, they have some sort of mixing distribution over the alternatives, which gives us this, what we're calling F1 of P, which we don't know. We can think of this pi as a empirical Bayes, like prior long-run frequency of nulls type of thing. And we're interested in, rather than estimation, we're interested in doing inference. So a simple bound is just to notice that since this mixture distribution has a uniform distribution in it, then that density has to be greater than or equal to this pi, the mixture that has a uniform at any point. And what Story in the 2002 paper suggested was that if the alternatives tend to have smaller p-values, then we sort of intuitively expect that this distribution of the p-values into the alternative is minimized at 1, right? If you look at the p-values near 1, those are the ones that probably came from the null rather than the alternative. And so that would be the best place to look for this infimum. So here we just have, we've changed the notation from, or changed the problem from conditional mean to densities, but densities are, kind of, density estimation is a lot like estimating the conditional mean. And we've changed the direction of this, but then you can see, here it's on the boundary again. And we have basically the same thing as before. So I won't go through the results. You can show that you can get a test that achieves the same rate. It would be an extension of this to show that it's formally that it's the adaptive rate. And probably in practice, if you had more knowledge about the alternative space, that might be something that you would want to use. So depending on how much you know about the alternatives, the notion of adaptivity is maybe a weaker result. But I think it's interesting that you can apply this same type of thing to this kind of different problem. OK, so to conclude, I've talked about inference on the conditional mean at the boundary, shown how to get adaptive one-sided tests and confidence intervals under a monotonicity condition, where we impose a small amount of smoothness. Applications include regression discontinuity, identification at infinity, and multiple hypothesis testing, and I guess anything else that has to do with inference on something in a boundary. And you can also think of this as an argument that looking at multiple bandwidths and just calculating a confidence interval that's uniform over bandwidth and just kind of reporting that is, in certain senses, in certain cases, kind of the best thing that you can do. So you can think of it as think of this whole talk as just a plug for my other paper with Michael Colasar.
OK. Thank you very much for having me, and thanks to the organizers for giving me the opportunity to discuss this paper. And I really enjoyed reading Tim's paper. This one and the follow-up. Actually, I do have access to a preliminary draft on the follow-up paper, and it was excellent read. I mean, as usual, it's great work. So the way I'm going to structure this discussion, just with the explicit goal of keeping you here as long as possible, will be first, I'm going to put Tim's hat. So I'm going to assume for a minute that I was technically able to write this paper. And assuming that, I'm going to try to sell it to you. So I'm going to try to make a point of why this paper is important and what you're learning out of it, beyond what Tim already explained. And then what I'm going to do is I'm going to walk you through the assumptions that he imposes to achieve the goal, or the two goals that I'm going to explain, or at least try to the best of my knowledge, explain. I'm going to try to disentangle which assumptions are crucial from which assumptions are actually kind of not very important. And then I'm going to try to make a point that even though Tim emphasized that this is the best thing that you can do, I'm going to pick up on something that Bruce said before, and I would say that, as usual, it's the best thing that you can do, conditional on having chosen a goal. And so the fact that you're choosing uniformity and certain type of uniformity and so on is great, and I support my friends who work on uniformity, but I also want to point out that there are other concepts of optimality, and some of them are decision theoretic based, other ones are not, and we still care about them as well, especially from applied work. So from the point of view of why the paper is actually really cool and important, I think that the best way to explain this is to separate two issues that actually are, in some sense, intertwined in the main results of the paper, as far as I can understand them. So one issue is kind of a logical inconsistency that arises in non-parametrics always, I think, which is this fact that we kind of all of us fool ourselves, and if you were really a purist, you would take this very seriously, which is the following. You typically assume a level of smoothness, and given the level of smoothness, you kind of do your usual bias calculations, and you somehow get this last term, which is a sort of a bias term, right? And then you balance that out with variance, and usually you put in a mean square error form, and you get kind of a bandwidth that is optimal. And then it's optimal in the sense of minimizing mean square error for a point estimator based on that non-parametric object. And then based on that, if you're really outrageously sloppy, you just put some hats on stuff, and you construct an empirical bandwidth. And then you go back and just plug it in on the procedure that you started with. But at that point, you kind of run in a logical inconsistency, because if you had that last bias term to construct the mean square error optimal bandwidth, one would argue, Tim would argue, I guess, is that you are being silly, you are leaving money on the table. You should use that last bit of smoothness actually to construct an estimator that behaves better. So in some sense, we run into this logical inconsistency that either we exploit all the smoothness to construct the best possible point estimator, but then we are unable to choose the bandwidth because we have nothing left to optimize with respect to, or we kind of leave some money on the table, we leave some smoothness out there, and then we use that to characterize the leading bias term and then choose a bandwidth that optimizes. In some sense, the procedure that he proposes, which actually builds up on a more recent literature in statistics, seeks to kind of give a solution to this problem, as opposed to just trying to plug in point estimation type optimal choices of bandwidth. You just try to do something else where the bandwidth is some sort of endogenously determined, trying to exploit this amount of smoothness without having to do these two steps that will run into this logical inconsistency. So that's point number one, and I think this point is well taken. So I've done this always, I teach this to my students, I'm very ashamed of that, but I will continue doing it because I think it's practically easy to explain, right? So, and also, in all fairness, it's kind of a philosophical issue, right? So how much smoothness you really have, how much smoothness you're willing to entertain, and what kind of estimator you end up with, right? What kind of weights this estimator is putting on the data that you're using. Maybe you assume that you have 15 derivatives, but if you use all 15 derivatives, then the polynomial that you end up fitting is kind of incredibly wiggly, and it's putting weights that are extremely weird on the different observations that you are constructing the estimator with. So there are issues here that go beyond the uniformity on smoothness point, but I'll take it. It's logically, I mean, I'm supposed to pretend I'm an econometrician, so I am supposed to obey by the rules that if you put assumptions, then you devise optimality, then you should work with that. So I'm willing to take that point. Then the second issue that this type of work that Tim has contributed to quite nicely is related to is to the idea of what kind of alternatives I can detect. And this relates to the issue of log n, right? So the way I thought about this when I read the paper was this idea that I can have a function that has a discontinuity, but right next to it, sufficiently close, there is another one that is continuous. And so there is no way that I can actually disentangle the two. There is no way I can test for discontinuity in a function. So essentially, unless I put restrictions on the class of functions on the alternative set, in the alternative hypothesis, I will be unable to test, or more precisely, I will have power equal to size for some alternatives that are sufficiently close to the null, where the null is this discontinuity. And so in that sense, I could convince my friends here to write a paper entitled On the Testability of for regression discontinuity designs, right? Because effectively, one would say that in regression discontinuity designs that I have contributed, and again, done the wrong thing here, one claims that you have confidence intervals that actually have power equal to psi for some alternatives, right? So in this sense, but again, this is a technical aspect. Sometimes we're willing to say, well, look, really, if the underlying regression function is really continuous and not discontinuous, but it's so steep, right? At the end of the day, from a practical point of view, from a policy point of view, does this really matter? Well, if you're a purist, it matters, right? That one is on the alternative set, the other one is on the null. But from a practical point of view, probably it doesn't matter much. But that's my take on it. What Tim does at the end of the day is try to handle both problems at once. So he kind of writes very carefully the null hypothesis of interest and then the alternative. And the alternative has to, in some sense, kick out some functions that are not going to behave well. And so the way that he does this is by putting some Lipschitz condition and then some monotonicity. And that, in that sense, I think it's super cool, right? Because at least it gives a clear interpretation of what kind of functions we need to get rid of the alternative set in order to achieve non-trivial power, and at which local alternative rate we can do this. And this is kind of the idea of log n, which I think is super, super cool. So here's kind of my take on this. So I'm not going to repeat what Tim said already, but basically the main two results that I think are kind of important is this idea of adaptivity. Adaptivity here means uniformity, right? But uniformity not on the data, well, maybe I guess it is on the data generating process, but it's in a very particular way, right? And so I'm going to talk about uniformity in a minute and my take on it. So my friends here really hate me from now on and ever again. I guess they brought me because of this. But anyway, so it's uniformity in a certain sense, right? So here we're moving, we're searching for the worst case scenario among a very particular class of functions, and those are the ones that are characterized in this set sigma. We're essentially saying that I'm going to play with the degree or the Hölder coefficient there, the beta coefficient there that controls this kind of a smoothness of the g function, as you said correctly, really locally to 0, which is the only place that we care about. And then you prove quite nicely that this log n is really what characterizes the type of local alternatives that we can handle. Okay, and then the other thing that he does is he constructs an adaptive to beta again, right? So I'm trying to emphasize being pedantic with the parentheses or whatever. The beta, so the uniformity here is with respect to beta, really, at the end of the day. Okay, very good. So what are my take on the limitations? So some of the things that Tim said, I'm going to just repeat here, and I think we all, well, not all, whomever had the courage to go to the proofs will see that shape restriction here is crucial. So monotonicity or some other form of kicking out these functions out of the H1 set needs to take place. Otherwise, you're not going to get more than power equals size here. So that makes sense. And monotonicity is kind of interesting. And honestly, in regression discontinuity science, at least, which is the only thing I maybe know something about, it's kind of reasonable. It's not crazy. So I will take that. The one-sided confidence interval thing, well, I mean, I don't know. I guess you can work more on how to actually make this two-sided, or maybe perhaps it doesn't really matter much. It's a discussion that we can have. The adaptation to beta, more importantly, something that you just briefly mentioned, but I think is very important to say, is that many times, even though we do not know the Hölder coefficient, or maybe we don't know the degree of smoothness, it's definitely the case that we will have more than just Hölder continuity, right? So in most non-parametric problems, we are willing to assume one derivative, two derivatives. So these are very a rough subset of the problem. So I would say that regression discontinuity designs, where effectively, at least partially the selection process is being seen because the running variable is capturing this endogeneity. I mean, you see almost all applications and they look pretty smooth. So I wouldn't say that they're as rough as this type of assumption, but I understand why it's there. Then Gaussianity, I think is actually more crucial than Tim confessed, and I'm going to make a point about this, but it's a debate, right? So we can discuss about this. And then there is a boundedness assumption there that is floating. I'm still trying to convince myself if it is important or not. He puts the same constant for everything, which I guess it makes it beautifully nice to see, but harder to understand which one is biting at the end, right? So is it biting the possibly champ in the CDF, or is biting the bounded variance? I pick at the proof, and I think it's the bounding variance part that is biting here, but I may be wrong on this. And then finally, what I think is very, very important here, and in some sense is handled appropriately, but it may lead to something that is extremely conservative, is a bias. So bias here is handled essentially by the monotonicity argument, which is correct, and I understand, but effectively that doesn't take away the fact that the function could actually be rapidly increasing, in which case this bias is going to be there, and you're going to have a huge, very conservative type of confidence interval. So again, you could reduce this easily by fitting a linear or quadratic, and then handling the smoothness that way. I don't know. I would think a little bit more about the bias itself. Now, in terms of the big picture thing, right? So someone said yesterday that discussants are supposed to give big picture thing. I cannot give big picture things to myself, but whatever. I'm going to try here. So the obvious first question is a general one. So why is adaptivity important, right? So, and this goes back to the idea of why is uniformity important. Maybe, look, if I leave one derivative on the table, it's okay. I mean, tomorrow the sun is going to come out, you know, like it's not the end of the world. We don't really need to be that extreme, right? Or maybe we do need, I don't know. So maybe, I mean, if I put my hat, the Niemann-Pearson hat, then I really want to control size, right? And then I'll do whatever. If I give up on power altogether, well, who cares, right? Or maybe not. Maybe I'm willing to have a little bit of size distortion and trade off with some power there, right? So there is some loss function that I understand the profession pushed us in one direction, but but there is something to be said about being a little bit more flexible, especially in a conference where we're trying to connect perhaps with practitioners. So given that you agree on adaptivity being the only important thing in the world, then number 2 would be, can I construct an adaptive procedure? And this is a question about existence. And so you prove existence, so that's great. Now, the only thing I didn't like, or not like, I couldn't get myself out of the paper is the intuition of how the procedure was constructed. So mechanically it works. But if you could explain what was the intuition, why is this one working and some other is not working, then maybe I learned something for the next time, right? So the idea of how this was constructed, which is number 3 here, I think is very important. And then also, I mean, at no point in the paper it says, and I don't think it is true, that this is the only one. So something about how we could rank this type of procedures, even if we are setting it on adaptivity as a measure of correctness or importance among procedures, there still may be more than one. And so one could say, how could I rank another one? Could I take the 2 that I have and linearly combine them in some clever way? Can I do something like that? The final point I want to make is that look at the procedure that Tim proposed. Basically, the procedure is swooping over a lower bound and an upper bound, and eventually this lower bound here is set to 1. So essentially, you're running from just one observation all the way up to all n of them, which makes sense if the Gaussianity is there, because then it works. But obviously, if yi's are not Gaussian, then when you take the very first observation, I mean, all hell is loose, right? So what I would say here is that, in some sense, even with all the results on adaptivity, we just move the problem from choosing the bandwidth to choosing the lower bound on where we're searching. And so there is still a tuning parameter here. It's a different one. So I'm not saying, I believe you when you say that it's better than everything else, but you still have a tuning parameter. The tuning parameter here is how far deep in the lower bound I go. I mean, without Gaussianity, I guess 30 is what I teach my undergraduate, so I'm happy to plug in 30 there. But then if you plug in 30 and the observations are sparse and the underlying regression function is not flat, then you're going to have a bias, right? And so if I move far, far away and start searching out there, I'm going to have a bias that could give me something that is, at the end of the day, incredibly conservative. So I think there is some things to think about, and I think this refers to the final point. And then I'll stop, because the other one was just to try to implicitly sell my own work, so I'm going to skip it. Okay. Thank you.